Yep. Right, so the rules for this are that it's a chess timer talk, and you get to talk as well. And I think there's a counter there. Which one's mine?
Lost a second.
Yeah, by explaining this, I'm wasting my time, so that's not fair. But the idea is you can interrupt at any point, and sort of if you say something that triggers my answer or my comment, then I think that still might count as your time. So you have to be careful about what you say.
The goal is like to use. Oh, you don't have to do. That's nice of you. Thank you. The goal is to use the opportunity to ask him questions so that he doesn't run out of time to explain the things that he wants to explain, right? So he's got a 40-minute block, you have 20 minutes of question time, and he's got 20 minutes of solo speaking time. So help him out by asking him questions.
Yeah, but when he's answering a question, whose clock is running?
Yours, audience.
Okay, it wasn't always done that way in some of the sessions.
Others are trying to be creative with it.
If it turns out that there's sort of more interaction than the time allows, then I think I'm happy with that.
Then that's a win, yeah.
I can break the rules if I want, in your favor. So the topic, and I sort of wanted to do this as a chess timer talk because I thought this is something that will trigger a lot of discussion, and there's a great audience here who will have lots of interesting ideas on this, I think. Just to check, how many people here are sort of primarily academics? How many people here primarily work in the industry? Good. How many people are persons of leisure? Perfect. Okay, so I call this the search for fundamental software engineering principles. The search is the keyword there. And I'm going to start by sort of introduction. What is a fundamental principle? So if you look at computer science, we have things like the halting problem, which is a fundamental computer science knowledge. If you go to university, they'll teach you what this is. And it says that it's impossible to give a program that for any other program, P will decide whether P terminates or not. Objection? Yes?
You have to include the data.
Yes, you have to.
With its data.
It's simplified version, but yes, it wasn't written fully formally, and the point is you have to write it fully formally for this to actually be a fundamental computer science knowledge. The reason why I was showing this is that this is something that will remain true regardless of what new software development methodologies will be invented. If somebody comes with much better source control, this still holds true. If somebody comes up with a new programming language, this still is true. And this is what we teach as a computer science knowledge. Yeah.
So, I mean, that assumes that the programming language is Turing complete, right? Yeah. So we might have some sort of configuration language which we can analyze.
No, the great thing about this computer science knowledge is that it has so many assumptions that are explicitly stated in a textbook, not on my slide, that mean that it is actually going to be true. It just might become unimportant. But it's still going to be true, at least. So the point I want to make here is that if we look at what some of the software engineering courses that you might find cover, or what we consider as software engineering, are these things like Agile and Scrum methodologies, or various modeling methods like UML, which apparently specifies the exact shape and size of the legs and arms of the stickman. It does. Various OO design patterns, or tools like Travis and Docker, and that really doesn't strike me as being on the same level of sort of fundamental knowledge as what I was showing before. So the sort of open question here: what would be a more fundamental software engineering knowledge? And I think the sort of interesting questions might be to ask along the lines of the halting problem, what is actually impossible to build? Or are there any sort of guarantees that we can give about building actual software? And I think my sort of two early points is that I don't think this is a formal mathematical problem like what we do in computer science, in theoretical computer science. And can we say anything certain at all about this topic? I think that's a sort of open question here. So just before I pass this over, I have two more things about fundamental knowledge. One is that I think we really should be looking for things that will remain true or relevant in 100 years, and the motivation is those might be the kind of things that are worth teaching. Over to you.
Would you say the problem is similar to contrasting computer science and software engineering versus, let's say, any of the kind of physical engineering, chemical, mechanical engineering, and how the industry works there? Or one example that a colleague of mine recently gave was accountancy. Like, if you have, so let's say, a chartered accountant's degree, people don't ask you to do accountancy in the interviews, whereas even with a computer science degree, we still ask people to do basic coding interviews.
Yeah, so one of the analogies was sort of mechanical engineering. And I'd say it's sort of, I guess the sort of question is is there enough sort of structural similarity between the kind of things that mechanical engineers deal with? Yeah, I don't know. That one is tough. And I don't really know enough about engineering to have a good thought on that. Is there a comment?
Oh, just another question. So when you're done.
Yeah. And I don't know how accountants get hired, if they just do sort of math puzzles, or if someone gives them like a stack of invoices and they have to do it. But yeah, I think that's a sort of two interesting fields to look at for inspiration.
So I understand your kind of intent of not wasting the teaching time at universities and stuff that's outdated when you leave the university. On the other hand, there is a tension because in industry we want people to leave university knowing something they can use in practice. So how would you resolve this tension?
I would resolve the tension by saying that's not what universities are for. But
so would you say, I mean, I understand that, but there is still the tension, right? So there are people who go through a 5-year education, go to industry claiming that they are, quote, employable, and of course it's not like they're not at all, but you know, that there is a tension. You can't just say, I don't care.
Well, I just did that.
Yeah, I know. I just don't think.
No,
I just think that this
too much of
you're
right, because if you look at our university's website, it will say exactly these things.
I know.
It will say we will teach students how to be efficient in industry from the first day they join the company, and I think that's a sad state of the academic world these days. I think what I would say is that we want to do things that will make those students, when they start working, give them something that makes them better. And I think things like computer science, sort of theoretical computer science, sometimes you might actually have to implement some algorithm and then it's great, but I think it's just a sort of extra thing that makes you a better thinker. And I think there's sort of one area for this is computer science, but I think it's a sort of interesting open question that I'm trying to pose here as what would be the sort of more extra things that we can offer students that are really related to the more applied side of software building.
As a data point, medicine. you think would be very vocationally oriented course, but at the end of a medical degree, you're not licensed to practice.
Medicine is really interesting field because it's also where you really, really have to be careful about getting the vocational skills as well. So I'm not saying that software, sort of foundations of software engineering should be the only thing that universities do. I think there's plenty of space for sort of doing projects that will sort of train students in the vocational side of things. But I think that the whole idea that that universities can teach people so that they're productive from their first day is just wrong, because even if you switch as a professional, if you switch companies, they'll be working differently, and you have to learn some things, and it's sort of about building the right foundations, I think. Any other person? Yeah.
I didn't want to leave undebated that point about mathematics not being considered a fundamental.
Sorry?
I don't know if maybe, I don't know if I understood the slide correctly, but I thought that you were positing that the mathematics wasn't like such a fundamental tool.
Yeah.
So my point is, I think it's a bit of a narrow view. There is a narrow view of mathematics, and it came up this morning with Cynthia's amazing presentation. But I felt like, well, she didn't push back when somebody came saying that logo for constructing language wasn't maths, and I think it's a great example of math of combinatorics. It's a very important, basically, it's not explained properly in CS, and how to combine with verbs, and that's basically a set of nouns, set of verbs, and combinatorics. That's absolute math, I think. So. Yeah,
I think that's a very good point, because the sort of math I presented was really a very much a caricature. So the reason why I was sort of saying here that maybe math isn't the only part of the answer is because I'm sort of trying to, there's theoretical computer science which has its particular math, and that we know how to teach, we have lots of knowledge in that space. I think there's sort of a lot more of math that we could have, like the sort of along the lines of what Cynthia Solomon was talking about in the morning. But I think there's also sort of more stuff that we should have along the lines of what I'll say a few words about next at some point, unless there's more thoughts, comments. Yes, one here.
Sociological, because you have to talk about teams and how they work together and how they share knowledge, and you have to talk about organizations and how they work and commercial constraints and things like that. And you're getting, with all of those, you're getting further and further away from some sort of precise discipline where...
So can we not avoid being sociological? And I think the answer is we can't. And that's what I think we actually need to do, or we need to acknowledge that. So when I was sort of thinking about this idea of fundamental principles, what I really sort of ended up thinking is that what we need to do about software engineering is really sort of acknowledge that everything in that space happens in some context, and that's if you look at any sort of technological or even sort of process aspect of software engineering, like say the waterfall. That's something that happens in a context, and I think understanding this context is very, very important. So what my sort of tentative proposal for what we should be doing in software engineering is really to have more sort of historical and critical analysis of software development tools and practices, including the sort of historical context for those. And I think that's something that computer scientists who are sort of trained in this ahistorical thinking are very bad at, and we should work hard to actually learn our history and not just because history is fun and interesting, but because it's actually something that we fundamentally need to understand what we do. I think one side of this that I think is really interesting is where the phrase software engineering even comes from. And there's a really nice book called The Computer Boys Take Over, which documents some of the early history of the social side of programming. And it starts with 50s, when programming was black art, a private arcane matter, and each problem required a unique beginning at square one, and the success depended primarily on programmers' private techniques and inventions. So this was very sort of individualistic, hard to control way of working, and the term software engineering became popular thanks to a NATO 68 conference on software engineering. They sort of started with the name and then said, we want programming to transition from craft for long-haired priesthood. I don't know what's wrong with that. To real engineering discipline, but that's the military folks saying this. So, but I think that the really important thing here is that this is something that sort of this idea to have a real engineering discipline is a response to a particular situation that comes from sort of businesses who at that time were really much less democratic, I'd say, than what people might be experiencing these days in some fields, and the military. So obviously that's what they want, because they don't want to have sort of creative programmers inventing new amazing features. They want to build a rocket that will hit the Soviet Union.
That conference was where the term software crisis came from, and the point was that software was being defined and then written, but not ever being successful, not reaching what was asked of it.
Yeah. So the book I mentioned has a sort of long history of that, which and I think that there's one more bit to this conference which I find amazing, which is that in 1969 there was a follow-up conference which was widely regarded as a failure, because the first one was very good at defining what the sort of problem is, and then they gathered again to find solutions, and nobody agreed with anyone on anything, and no solutions emerged from this. And I think one thing that sort of happened there was that there's people with different sort of cultures. There's the sort of mathematical formal culture where people sort of were looking for formal mathematical approaches to programming. So if you were here for the previous talk, that would be a clear illustration of that. The other approach was the sort of more business or management culture, which tries to find sort of ways of organizing the company so that it doesn't really matter whether a programmer, so that the sort of individual features of a programmer are controlled for by the system. And every time I sort of read a rant on Hacker News on why do we interview programmers by giving them these mathematical questions as puzzles, I think that's a sort of nice illustration of this cultural divide, where we work in one way but interview in the other. So I think this sort of historical context is really nice for sort of understanding what's going on, because if you know that this idea of applying industrial methods to software production is something that comes from businesses and military who care about control over budget, scheduling, and workforce, and also sort of control over the individuals that are involved, then things like some of the sort of heavyweight software engineering processes actually make sense in that context. And I think that's one sort of case study that I think is a valuable fundamental lesson about software engineering. Yes.
So this claim that it's about eliminating the reliance on individuals, did you come up with this, or did the conference state that as a goal? Because I think it's more about scaling things up. It's not so much about not wanting to rely on people. It's more about how do you do this with 50 of them.
So I think that the control over individuals is what I got from the Nathan Ensminger's book, Computer Boys Take Over. So I don't know if it was sort of explicitly stated in the conference. I think he has a bunch of other sources that he's using. So so he does. I refer to that book with that idea, and I think partly it was more sort of sociological, where the programmers were seen as these sort of weird types that are expensive, and you can't quite train them, or you don't know how to find them. So there was a lot of. I think the perception was that way of treating programmers is sort of introducing a lot of uncertainty. So maybe it was sort of less about sort of controlling people, but more about controlling the uncertainty, I'd say. Which I guess is something that we sort of struggle with still. And that was one approach to controlling uncertainty, and the sort of modern agile methods have taken a different perspective on that. To the same goal, yeah. And I think understanding this goal and that there's sort of different approaches towards addressing it is actually one of the sort of fundamental ideas that we can think about.
Yeah, very quick counterpoint regarding this conference. There was a really interesting keynote in Lambdale last year by Pavel covering the conference, and he claimed that one of the conclusions were very favorable to iterative processes and agile, but somebody took the waterfall, but it wasn't waterfall at all, what it was suggested in that NATO conference. So that's a very interesting talk. I mean, he highlighted some things that were much more very agile in nature. So
yeah. No, I think what was interesting partly about the conference is that there was a lot of sort of plurality in the ideas, and now you can go back to it and take the bits that you find interesting. And all right, so the other thing I wanted to mention is, I think looking at this sort of context and history, we can also find a few things that I would say are getting as close to being fundamental principles as we can get. And some of those are around complexity. So this is another opportunity for disagreeing. Do you think it's sort of harder and more complicated to build a chess engine that will consistently win against grandmasters, or to build an accounting system that calculates VAT in the UK and France? Who thinks chess is harder? Who thinks VAT is harder? Yeah. So I put up these two because I think what I was doing here is slightly cheating, because the kind of complexity involved in these two are very different. And in the chess, it's really the sort of building that algorithm that will do it is hard, but the specification of, or the sort of, the constraints coming from the real world are very simple. In the second one, the algorithm is probably quite simple, but the sort of context that you're operating with is very complicated. And I think in computer science, we're very good at sort of understanding the chess kind of problems with theoretical mathematical approaches, but there's sort of what we can say about the kind of problems on the right is a lot more open-ended. And there's a well-known and not as widely read as it should be read essay from Fred Brooks, No Silver Bullet, which is based on his experience building the IBM 360 operating system. And one of the really sort of interesting aspects there is his sort of analysis of where does complexity come from in software. And he has this summary that much of complexity that software engineer must master is arbitrary complexity forced without rhyme or reason by the many human institutions and systems to which his interfaces must conform. So this is exactly the sort of UK and French government creating new VAT laws that your system has to deal with, and it changes every year, and sometimes in the middle of year when there's Brexit and things like that.
Just out of curiosity, maybe this is a good example. I generally agree with this statement here, but what do you think makes this a fundamental principle rather than just another argument somebody might make? Like today, people make all kinds of arguments like this on a blog post. What makes it fundamental?
Why do I think it's fundamental? I think because I think this is a fundamental observation. Because I can't think of a software system that wouldn't have that sort of interfacing with the outside world. And there's sort of, the case of chess is where the outside world is really restricted. But I think as long as we're sort of talking about software systems that are made to be used by humans for something, then this observation is something that will be true about the system. So that's why I think this is a sort of important thing. If anybody can think of a way of, well, we could have a more controlled society where nobody is able to force arbitrary complexity on our software systems, but I don't think that's the kind of society we want. Right? Yes. This chess timer thing really involves a lot of running.
To what extent is this statement true for something like civil engineering? You're building a bridge.
Yeah, we are back to bridges. So I think that the kind of messiness that bridges get exposed to is maybe more understandable. Like if you're building bridges, you have to deal with the sort of physical reality and earthquakes and other natural disasters, and but the way people will use the bridge is relatively predictable, I'd say.
But okay, there'll be institutions like lawmakers who impose their own constraints on the way you build your bridge. And
yeah, that's true. That's true.
So there's the whole,
there's definitely a lot of other sort of human institutions involved.
But civil engineers aren't necessarily having the same sort of crisis about how to go on with their fundamental principles.
Yeah. There might be another thing, which is the sort of changing over time. So a lot of software has this sort of problem that when you start building it, you're building something else than when you sort of continue building it half a year later. And that may be one difference there. But yeah.
Just about building bridges, isn't it also the difference by nature in the fact that the problem domain of building bridges is much more understood and smaller, and is also benefits from an order of magnitude of more human experience? Like humans have been building bridges for thousands of years, whereas software has been existing for tens of years. My argument would be, if you look at, for example, parser or lexical analysis, it's a problem domain that is understood. It is rarely a problem of contention, and we have developed tools such that it does not become a problem in software. Would that be a correct analogy for you, as making a parser is just as making a bridge. We have experience, we understand the problem domain, and we have tools to make it not a problem.
Yeah, I would agree with that idea, because a lot of the sort of complexity in software comes from sort of just having such a vast state space of possibilities. And I think in a sort of more controlled domain, like if you're building a parser, then you can rely on more sort of experience in that specific field. And parser isn't going to become something completely different.
I think one of the big differences to bridge building is that there are actually norms and standards, and the engineers are proud if they stick to them. They don't try to be creative, they don't try to be new, right? And in software it's really different, which is an argument for your principles, because they could be something slightly analogous.
Everybody will have to watch my talk before becoming a software engineer. Like it. So I think there's sort of two bits about complexity which I think are interesting here. One is this Fred Brooks idea that there's essential complexity, which is something that sort of comes from the problem you're addressing. So if you're building a VAT calculation system that should cover the whole Europe, then there's sort of essential complexity coming from this very problem that you're solving, and there's quite a lot of it in a lot of software systems that interface with human society. And then there's accidental complexity, which is what comes from imperfect programming tools. And one of the sort of points that Fred Brooks is making, that you can't make programming or building systems orders of magnitude easier just by reducing the accidental complexity. So even if you switch from say, JavaScript to writing all your programs in F#, then it might reduce your accidental complexity by a factor of 10, but that still means that the whole sort of complexity of your problem isn't going to reduce by an order of magnitude unless the essential complexity bit of it is very small. So his summary is there's no single development in technology or management which itself promises even order of magnitude improvement within a decade in productivity, reliability, and simplicity. I think he was very optimistic with the within decade. But why I'm mentioning this is because I think this is actually sort of analyzing the software development problem from a perspective where sort of he does very thorough logical thinking to talk about our discipline and about our sort of constraints, and it's not as certain as say the halting problem, but it's as certain as you can be within the scope that you want to talk about here. And since we were talking about the bridges, I think there's another interesting comment on complexity that comes from the US trying to build anti-ballistic missile system, which was called Star Wars. And this was supposed to be a system to shoot down Soviet nuclear missiles. And there was a long debate on whether a reliable system like this can be built. And one of the comments on this is coming from Dave Parnas, is analysis of why are digital systems actually more complicated than anything we've done before. And he has this sort of categorization where analog systems are easy to deal with because a small change in input will sort of, you can control how small change in input produces a small change in output. And that's something you can calculate with sort of reliability intervals and so on. Now, with digital systems, it gets harder, but if they have repeated components like CPUs, which is just a bunch of transistors, well, bunch is a bigger bunch of transistors. But there's repetition in that, so you can sort of, it's not linear, but you can fully analyze states of some of the subcomponents and then look at how they compose. The problem with software is that it's digital and non-linear, but it has no repetition in it, or very little repetition in it. So the state space is actually much, much bigger than anything we do in other areas, and there's no easy way of reducing that state space. So this was one of the sort of motivations for saying the Star Wars system will have this digital, non-repetitive qualities that are really hard to analyze. And the other sort of comment from that time was this idea that complex software can only be mastered if it's developed progressively with the aid of extensive testing and then operated more or less continually in a somewhat lenient and forgiving environment. So this thought was mostly based on sort of empirical analysis or learning from past experience of the field, and pointing out that you have all these constraints that you have to hold if you want to build a system reliably. The sort of case of nuclear ballistic missile defense was that since we have no planets on which to fight trial nuclear wars, testing the system is impossible. That's one point. The other was that it's a case where the environment changes faster than your system can react to. So if you sort of start building a defense, then the Soviets will build a more efficient nuclear missiles that will circumvent your system, and your rate of the rate of building the defense is sort of smaller than the rate of building the offensive systems. So that's one case where again I think we're getting at some fundamental idea that's sort of based on thorough logical thinking about the way software works. And I think this is another sort of case study that I actually did teach to my software engineering students last year.
But back that one slide, you've cherry-picked somebody there.
In this one?
Yeah, I mean Dijkstra would say the opposite.
Yeah. Well, Licklider would say sense. How do you? I think this is. So what would my reply to Dijkstra be? I think a lot of his commentary often comes from the perspective where you have sort of small interface with the human society and human reality, and I think this is a nonsense if we're talking about the sort of controlled mathematical world of chess. But I think what Licklider was saying here was more reflective of the kinds of systems that interface with human institutions and human world. So my answer would be that if you can sort of this boundary between the human world and the formal world, if you can control it, then this doesn't hold, and you can build reliable systems formally. But I think if we can't control this boundary, then we're getting to this kind of world. So that would be my interpretation of the debate that the two people would probably have if they were standing here.
So we're seeing complexity of different sources as the problem, and we're whinging about this, but what's the answer? I mean, is software engineering going to have to find a way for even individuals, let alone teams, it's even harder with teams, even an individual can get lost in a software project due to being overwhelmed by complexity. Because you don't know where to start, you try one thing, you know how it goes.
Yeah. Yeah, so what's the answer? I think I have 0 minutes. No, this is yours. Ah, cool. I'll tell you the answer on my time. Well, you have 8 seconds. So I think the first thing we need is to sort of acknowledge that this is the case and actually sort of realize that we are dealing with, I think if we just sort of understand that there is this source of complexity that we can't control through just formal methods, and programming is really sort of as much human endeavor and sociological endeavor as sort of formal endeavor, then I think we're finally going to realize that this is a problem we have to talk about. And the other thing that I find interesting is all these sort of the fact that software engineering was really a response to a particular context where a lot of the focus of that was on controlling and being predictable. I think that sort of defined that field for a very long time. But equally, you could use plenty of other metaphors. And one thing I find really sort of interesting source of ideas is work on urban planning, where people deal with these very, very complex systems of unorganized complexity. Is this a sign that I should stop? I know I should, but so I think we probably need to acknowledge that this is a problem, and I think we should be looking sort of outside of our narrow scope to for ideas. So in urban planning, nobody will try to model a city as a sort of model city in Coq and give you a formal proof that it works, right? There's sort of other interesting approaches and methods that are more focused on looking at individual cases and understanding those, and looking at the complexity, not of the whole thing, but of a part of the thing. So that might be one answer, but I'll end with a quote from Bruno Latour, who says who has this nice book, We Have Never Been Modern, where he's looking at a lot of the sort of interfacing between science and human society. And there's a nice summary of what he's saying, which I think is really applies really nicely to programming, which is that we must think of this parliament of things where natural and social phenomena and the discourse about them are not separate, but are hybrids made by this interaction of people, things, and concepts. And I think this is really what software engineering should be looking at.